Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based course, and as always it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step one aside as we jump into the beginning of chapter 5 on exponential and logarithmic functions. This is in the Big Ideas Math Integrated Math 3 textbook, and section 5.1 is on what's called the natural base e. Literally the letter e, not a variable but a constant, much like pi is. It's an irrational constant in fact, and it's the natural constant. So we're going to talk about that. This one is more focused on exponential functions as a whole, and throughout the rest of the chapter we're really going to dive into logarithms. If you think about it, we've done exponential functions quite a bit now. Back in IM1, we did in IM2, and even in IM3, I mean, we did a little bit of graphing here and there, but we also just dealt with rational exponents in the last chapter. So everything that we've done building up in an exponential format has led to this, including their properties. And when we start learning more on logarithmic things in future sections, I think starting with 5.2, hopefully everything we learned before will help make sense of it. But everything we did with exponential functions should work here and now as well. Some things with graphs, but they all have to do with this natural constant e. So if you want to jump to the description section down below and download this PDF, you may go ahead and begin with that, and as well as follow any timestamps to any parts that you'd like to watch on this video. I'm going to start with the lecture portion, then we'll go to the problem set. I don't remember how many problems, I think it's in the 40s, but we're going to start with the lecture portion here. We're going to define and use the natural base e. Again, e is not a variable, it is an actual number. Well, I'll even show you where to get it in the calculator, and we'll show you how the number comes to be. We're going to graph natural base functions, so actually draw them on a graph, and this is where a table can be required or not, but the calculator really has to be in use because the number is so particular. It's such a irrational decimal, and solve real life problems, so word problems. E is really used in continuously compounded interest word problems, so things with money and growing that money. Okay, the natural base e, the history of mathematics, is marked by the discovery of special numbers such as, like I said, pi and I being imaginary. Although another special number is denoted by the letter e, the number is the natural base e. The expression 1 plus 1 over x to the x power approaches e as x increases as shown in the graph and table. Yeah, when you think about what's happening here, 1 plus 1 over something raised to a power, what happens when you do 1 plus 1 over 2 squared, 1 plus 1 over 3 cubed, 1 plus 1 over 10 to the 10th power, 1 plus 1 over infinity to the infinite power. And that's really what's going to happen here. Eventually, over time, this graph, it gets bigger, the y value gets bigger, but it converges to a value. At some point, it approaches actually an asymptote. It approaches an asymptote to a point, and that number happens to represent e. Now, what is that e value? As you see these x values increasing more and more, here's when you plug in 10 for x, and 100, and 1,000, 10,000, 100,000, and 1 million, you start to see it converge toward this number here, 2.71828, and it keeps going in some sort of way. If I scroll down more, here it is. As x approaches infinity, then e is approaching this number here. And again, it's irrational. It never truly repeats itself, despite the fact you see this like 28182. You see a lot of 2s and 8s and stuff. There's the number there. Now in your calculator, if I go to this right here, in your calculator, if I do e is above this ln, and we are going to be using this ln button literally for ln later in the chapter. It stands for natural log. But if you hit second in that button, it shows e, and it's asking for a parenthesis, an exponent. To what power? Let's say to the first power. Here's what that number is going to be for us, at least, e to the first power. So it only shows so many decimals, obviously, but that's the natural constant and natural growth. And if you've done if you've done compounded interest formula things, then it should make sense in why we might refer to compounding something infinitely over a certain amount of time, over an infinite amount of time. Now, e can be used just like any other number. It is a number after all. So if they ask you to do things such as simplify these numbers, and remember, we don't have to use the calculator for these parts, it's just use e as its base. E cubed times e to the 6th, treat it like a 2, treat it like an x. You get to keep the base and add the exponents, and it becomes e to the 9th. Now, e to the 9th is a number, and they're showing you over here, if I do e cubed times e to the 6th, I get this number, e to the 9th, I get this number. It's a number. I don't know if they're asking you to round, it doesn't sound like it, but they're just asking you to make sure that you can treat it just like anything else, and it can evaluate if we choose to make it so. 16 e to the 5th over 4 e to the 4th. 16 over 4 is 4. E to the 5th over e to the 4th. Remove 4 of these e's and 4 e's from here. You're left with just 1 e. So 4 times e is there. I'm not going to calculate it, but it's probably a little more than 10 because e is around 2.7. 2.5 times 4 is 10. 2.7 times 4 is a little more than 10. Probably around 11. And 3e to the negative 4x power squared. If you would like to, you can square each individual part, square the 3 to get 9, square e to the negative 4x, and these two multiply to become e to the negative 8x. And of course, our simplification rules ask you to turn negative exponents positive, in this case by bringing the e base with its positive exponent down to the denominator. So simplification is no different than what we would do with actual x variables in that way, and if they ask us to evaluate, we absolutely could, because those are the numbers. Let's move forward to graphing natural base functions. Now, they're probably going to use a table, which is perfect for the example set, and I'm going to use the idea of tables, or at least the calculator, to get some values out. When I graph, before I talk about their thing, when I graph exponential functions, I get a reference point, a starting point. It generally has to do with the y-intercept, or it depends on if we do any shifts. Looks like they're doing y-intercepts at 0, so this is pretty straightforward. So I'm going to start with a y-intercept of whatever a represents. A, in this case, a looks to be 1, so I'm going to start with that 1. And then I'm going to multiply by my base value, my growth factor, decay factor, every time x increases by 1. Now, in this case, we have to multiply by e each time. When e is around 2.7-ish and you have to multiply by that each time, you can see you're going to get weird decimals each time. So I'm going to use the calculator for some of those, and they're going to show you a little bit what this looks like. A function of the form y equals a times e to the rx power is called a natural base exponential function. A represents not only your y-intercept, but really what happens when, whether it's positive or negative. They really refer to positive values because we really use e in continuously compounded interest with money. So I think they're really going to refer to a lot of positive a values. If they do a negative, hey, we'll flip the graph over and we'll go down this way. But when a is a positive number and when r is greater than 0, r being in the exponent this time, it'll have exponential growth. That's because you're raising e to positive powers as x increases. If r is less than 0, a negative number, you're raising e to negative powers, which means you're dividing by e each time x increases by 1, which means your value is going to shrink. It's going to decay. Not become negative. If you know exponential functions, there's growth and decay toward an asymptote, and it'll get closer to 0 as x goes along. So taking a look at a couple examples, let's look at y equals 3e to the x power. Again, when I do this, I'm going to start with plugging in 3 there as the y-intercept. Boom, right there. When x is 0, y is 3. Boom, boom. And then every time x increases by 1, you're multiplying by another e. So I understand table usage here. It totally makes sense because these numbers are not pretty. And going to the calculator, I'm going to have to do a whole lot. So I'll probably use the graphing calculator itself. I'll go into here. I'll, go y equals, and if I do 3e to the x like this, I'll probably just go to the table. I'll go to the table and I'll get some points here from like -2 to 2, something like that, and I can just plot those. And you can see the numbers on this table in a second. 1.1, 3, around 8.2-ish, and 22.2-ish. So when you look at them right here, it's the same set. 1.1, 3, and 8.2-ish, etc. Those are the numbers. We can plot them. We can get our graph, fit it within whatever window range we're going to do. I'm probably going to do the tall graphs so I can fit numbers up to past 15 a little bit. Here's e to the negative 0.5x. It doesn't matter that r is like a 1/2, a number less than 1. It just matters that it's a negative number, which will mean it's decay. So as x increases, then you're dividing by more e's, which means they get smaller. The general, because this is... actually, I'm not going to talk about it with this one. I'll probably do it with our own among these, but because these are going by 2, so never mind. But this is an exponential decay. They go by 2s each time for whatever choice they have, I guess, because it's half of a number there. So they just want to use that. They're talking about you can rewrite natural base exponential functions to find percent rates of change. So you can turn this product of the exponent into just its own little portion of the exponent raised to the x power to turn it into a number. So you can find out what percent loss this value is, for example. If we have to do some more of these, I'll explain it more in those problems. Solving real-life problems, this is where we talk about continuously compounded interest. You've learned the balance of an account earning compound interest is given by this here. I'm trying to remember when this was specifically learned, as in whether it was IM1, IM2, or something before it. But this is something with the principal amount, the interest rate, the number of times you're going to compound it throughout the year, and the number of years that you do it gives you your final accrued amount over that time. Now, as I stated, as n approaches positive infinity, you can divide your interest rate up an infinite number of times and compound it an infinite number of times throughout the year. That's where e takes form. Now, there's a proof to get from here to here based on n approaching infinity and approaching positive infinity that gets you to rewrite the formula as this. I'm not going to dive into the proof right now. I want to save lecture time. But this becomes a equals p e to the rt power, which looks a lot like the exponential function graph thing that we just saw before. I like to say as apert, if that's a way to remember the formula. Remember, e is your base value for the exponent. E is a constant. It's a number, 2.7-ish, whatever. Your variables are your principal amount, your interest rate, and your amount of years that you're compounding that interest. This is the most that you can get out of any interest rate given compounded interest because you're compounding infinitely you're dividing that interest rate to an infinite amount and compounding it infinitely. So 2.718 whatever, that number is the most you can get out of a factor out of compounding. So let's take a look at examples of that. You and your friend each have accounts that earn annual interest compounded continuously. The balance A in dollars in your account after T years can be modeled by this, which means you have a principal amount of $4,500 and your interest rate is 4%. The graph shows the balance of your friend's account over time. So we don't know that model yet, but we have some information. Which account has a greater principal? Which account has a greater balance after 10 years? So regarding principal, I was saying our principal amount is $4,500. Theirs at time 0 is $4,000. So we have a greater principal. Let's see where they say that on here. Your friend's principal is $4,000. Yours is... I can't seem to find the number. I don't know where ours is, but here it is. Our principal is $4,500, so ours is more. We have a greater principal. But over 10 years, what we have to do is substitute 10 into this equation for us to figure out what our balance will be after 10 years. It's 6,700-ish. And then your friends after 10 years at 10 looks to be over 7,000 something. Even if we don't know the model, we can see it's more than 7,000. Therefore, they say about 7,250. So therefore, your friend has more money after 10 years, even though we have a better principal. That must mean their interest rate is higher. Maybe it's 5%, something like that. Was there a second part? No. Let's see what this part's talking about. Because your friend's account has a lesser principal but greater balance, they're talking about average rate of change. They're averaging over time, although it's not linear, it's exponential. Over time, they're averaging 325, it looks like dollars a year increase. We're averaging about $221 a year increase. Remember, that's just a slope. That's just counting the rise over run over the course of those 10 years as if it was a straight line. Okay. All right, so let's get into the actual problem set. We're going to start with the vocabulary and core concept check. They ask, number one, what is the Euler number? Now, I don't know if they probably said that name Euler. It's a proper noun. It's someone's name. I forget their first name. They sound French. Euler's it's one of the fathers of calculus or something. I know I'm botching something when I say that, but the Euler number is E. I don't know if that just helps answer the question right there. And it's a natural constant. It's the natural constant, which kind of represents natural growth. It's about equal to 2.718 something as it moves on. So it kind of talks about continuously compounded interest and growth, how numbers can grow over time. E also has another really interesting principle to it. This is something that you're going to learn more in calculus, and we should talk about the graph thing later. But whatever y value it's at is the slope of the curve at that actual point as well. So when x is 1, y is e 2.71, whatever. The slope at that curve is also 2.7. It's really interesting on the things that e has and does and stuff like that. Anyway, so next question. Tell whether the function f of x equals 1/3 e to the 4x represents exponential growth or decay. Explain. Now, it's not about the 1/3. It's about that 4, actually. E will be what e is, which is a number more than 1. So as we raise it to a positive number as x increases, then that means it's going to be natural or exponential growth. Exponential growth because r equals 4, and therefore r is greater than 0. When r is greater than 0, then you're going to be talking about natural exponential growth with that. All right, guys, we're going to go ahead and get into the official problem set on numbers, 3 through 43. So there might be some good drill and kill here, but there also might be some great calculator usage and graphing. So hopefully everything will start to make sense before we hit the logarithms in the latter parts of the chapter. Without further ado, let's go ahead and get started. Okay, we're going to get to numbers 3 through 12 to begin with and simplify the expression. There's no calculator usage for these as far as I'm concerned. Kind of treat e like an x in a way where it is, well, it's just its own thing. So number 3, we have e cubed times e to the 5th power. You are, of course, keeping the base and adding the exponents. 3 plus 5 is 8. You have e to the 8th power. You can use it in a calculator to figure out what it is, but I don't think I will. Number 4, more of the same. E to the negative 4th times e to the 6th power. That's negative 4 plus 6, which is 2, so e squared. You could also do 1 over e to the 4th times e to the 6th, where then you do 6 minus 4, because division of your bases is subtraction of your exponents. You still get e squared. Number 5, we have 11 e to the 9th over 22, e to the 10th. 11 over 2 is 1/2. So eventually we're going to divide by 2. And e to the 9th over e to the 10th. You can do 9 minus 10. I tend to remove all the e's from here, remove 9 of the e's from there. You're just left with one of them. So you're just left with 2e in the denominator. The reason why I do that instead is because if I do 9 minus 10, I'm going to get negative 1. Then I have to change the negative 1 into what have you. I think that's a lot quicker for me to work off of. Number 6, 27 e to the 7th over 3 e to the 4th. I like these questions. Nice and brisk. 27 divided by 3 is 9. E to the 7th over e to the 4th. Remove all 4 of the e's on bottom and 4 of the e's on top. You're left with 3 of them. You have 9e cubed. Number 7. 5 e to the 7x raised to the 4th power means each part of this product is going to be raised to the 4th power, both the 5 and e to the 7x. Let's do this one step at a time. That's 5, to the 4th. That's 5 to the 4th times e to the 7x to the 4th. Now 5 to the 4th is 625. E to the 7x to the 4th means you multiply the 7x and the 4 together. These multiply and become 28x, so that's e to the 28x. There's a simplified version of that answer. Number 8. Same stuff. This time we do have a negative exponent. You can either treat it initially or ultimately. And I'll do it ultimately, or penultimately, what have you. I'll do it last. We get to do 4 cubed, which is 64, and e to the negative 2x to the 3rd power. These multiply, becomes e to the negative 6x. We would be done except the negative exponent, so therefore we need to bring the e to the 6x down, turning it positive. 64 doesn't go with it. 64 is not raised to a negative exponent, so that'll be our final result. Number 9, we have the square root of 9 times e to the 6x. Now, we just dealt with radicals and rational exponents in the last chapter, so we should feel comfortable on these and what's going on. First of all, when it comes to square root stuff, remember that is implicitly a 2. Now, the square root of 9 is 3, but the square root of e to the 6x means the 6x actually divides by 2, so this becomes e to the 3x power. You don't take the square root of 6, it's just that there. It's like if you raise it to the 1/2 power, right? That's the same idea. Number 10 is a cube root, and once again, the same idea comes in mind here, only now we divide by 3 with exponents, but we also take this cube root of 8. Now, the cube root of 8 is 2, so we get 2. And e to the 12x to the 1/3 power, or 12x over 3, is 4x, so we get 2e to the 4x power. 2 more in this block. Number 11, we have 3 things multiplied. We have e to the x power times e to the negative 6x power times e to the 8th power. Now, they have the same base, so we would add the exponents. If you want to write this in full, that's x plus negative 6x, or just minus, plus 8. As far as combining like terms go, this would become e to the negative 5x plus 8. Now, because these don't combine, I suppose this is one version of the answer. However, when it talks about negative exponents and such, and who's to say whether this is truly treated as a negative exponent or not? It's up to you. If we split these up again, though, then we can have one of them negative and one of them positive. And with the one, it's separated by multiplication of the e's, not the exponents, but the e's. And with this one being negative, we can turn it positive if we place it in its denominator. So we can turn it to e to the 8th over e to the 5x power. I'd say this is probably a better version of the answers. I guess this is one of them, but, as long as it has 2 separate terms, I kind of want to separate them, and I think that that's probably best of what they'd be looking for a question like that. I don't know for sure, but that's what I would be lending toward. If they want to keep them together, then we would have it like this, just because it's now 2 terms. So I'm kind of an either or, this or that. Number 12 may be the same. It doesn't look like anything turns negative this time, but on number 12, we have e to the x times e to the fourth times e to the x plus 3. And once again, everything adds together, so it's all about combining like terms. X plus x is 2x, and 4 plus 3 is 7. So, as one whole, it would look like this. And this time I'm going to keep it like that. There's no reason for me to separate it to two separate parts this time. I only wanted to this time just to kind of get both of the exponents positive. But with two terms it looks like that, two terms it looks like that, and that's where I'm going to leave this. Okay, exercises 13 and 14. Let's describe and correct the error in simplifying the expression. So we just got a good heap of practice on it. Let's see what went on here. Number 13, we have 4e to the 3x, all that squared. And they multiply the 2 with the 3x to get 6x. That's actually appropriate. What they didn't do, though, was square the 4. And this is actually a common mishap. This has nothing to do with e, but just with exponents themselves. The 4 never got squared. The 4 never got squared. Now, I want to state this once again. This is a very common mishap because students, individuals, people, learners, whatever, students tend to attach coefficients at the hip with variables, which means that they don't apply it to the thing instead of treating it like a product. If it was multiple variables, they would be fine with it. If it showed a times in between, they'd probably be fine with it. That was the same reason why when I was doing this problem set here, when I said you don't bring the 64 down, a lot of people would also take this thing and they would bring the 64 down with this because they attach it at the hip with it. Well, it doesn't work that way. This wasn't raised to that negative exponent. If it was, we should have raised it to the 6x power as well. And it's not doing that, not unless it's in parentheses. And this other one is in parentheses. And because this one's in parentheses, they're attaching it at the hip in a different way. When they see 4e to the 3x squared, they think of just squaring this guy right here, going like, the 4 doesn't need it. Yeah, it does. It's part of the product. Part of this product, so you have to do 4 squared times e to the 3x squared. Anyway, 4 squared is 16, and this is still e to the 6x. So that was the one mistake. It's a very common mistake. I need to state that again, so I'm glad that it's something that they brought up. And then number 14, e to the 5x over e to the negative 2x. And you would subtract these two exponents as you keep the base, so there's a good idea there. The problem is the denominator is already negative. So when we're the exponent. So when we subtract, we should be subtracting a negative. They subtracted, but with an already negative exponent in the denominator, subtracting a negative should become addition. So these exponents should add, not subtract. So you have one of two options. Either just as is, you turn it into e to the 5x minus negative 2x, which becomes e to the 5x plus 2x. Whoops, I was trying to write the answer. 2x or e to the 7x, which is the answer. What I tend to do with fractions is I tend to say, or turn a negative exponent positive immediately by bringing it up into the numerator here. So it becomes e to the 5x times e to the 2x all over 1. And then you get to the same result here, e to the 5x plus 2x or e to the 7x. Like that. I'm going to turn that one green just to show the alternative version of that. Okay, so either or, that's what we got to fix. It's not e to the 3x because of the subtraction. And those are things that I feel like they could have brought up in previous sections when we started talking about exponential properties. But they're just doing it with e. A lot of things they're doing with e that's like, hey guys, again, for now, just treating it like a variable as much as you can. And if we have to evaluate, we can do that as well. Either or. All right, 15 to 22, we are going to tell whether the function represents exponential growth or decay. And then we're going to graph the function. This is based on whether the r in the exponent of this function is a positive number or a negative number. If it's positive, it's growth. If it's negative, it's decay. Now, first one is y equals e to the 3x power. Because r is 3 and 3 is greater than 0, r being greater than 0, this is exponential growth. And we are going to graph the function. I'm going to use this kind of graph paper right here. Now, I'm going to use a table and write this thing down, at least the first time, or I can copy paste from the calculator. That might be even faster for me. If I go to the calculator, we just came off the lecture portion where we did one in the calculator here. Let's substitute e to the 3x power. And let's just go straight into the table for this. I'm going to be kind of senior lazy on this one. And it gets pretty big pretty fast, right? So when it comes to table, I'm just going to do this right here. I own the right to be lazy on this one. So here's e to the 3x power. You know, e again is 2.7-ish. 2.7 is already being cubed immediately, right? Because this is the same thing as e cubed to the x power. So e cubed, 2.7 times 2.7 times 2.7, guys, that's this number here, 20.1-ish. And then you raise it to powers like 2, 3, 4. Now you're squaring 20. You're cubing 20, 20.1-ish. But it's becoming massive really quickly. So there's very little on this graph that I can plot. Now, the first point I'm always going to plot is the y-intercept. This is the a value, which is 1. So e to the 0 power is 1. Times 1 is 1. And then e to the first power is 20. That's already above this graph. Here's 17, 18, 19, 20. So I'm going to just go in the tall fashion right there, way up there. The only other one I could even try to pretend to plot is 0.05. That's not 0.5. That's 0.05. That's 1/20th. That's how close to 0 this thing already gets. So this graph, tall as the dickens, I say. Tall as the dickens. We go all the way to infinity and beyond. Super duper tall graph. They probably want us to change some scales. Not going to happen today. Depends on how big the numbers get. But it starts to flatten towards 0. And if you know anything about exponential functions, you know converging toward asymptotes. These things will have asymptotes at y equals 0, the x-axis, so long as, so long as we, in fact, let me just cut off this part of, give me 1 second. Give me 1 second, guys, as I talk. So long as we don't have any vertical translations or anything like that. What I'm going to do in the future graphs on these is I'm only going to cater toward, it looks like all these are positive functions, so I'm just going to use graphs that look like this. Sorry, that was a little tall. Graphs that just look like the top half right there. So I'm going to get that one ready to go each time we have another problem. That's number 15. And that is exponential growth. This thing is going up as x. It's separating from the asymptote as x increases. Number 16. And here's the slowdown. Y equals e to the negative 2x power. Because r is less than 0 this time, this is going to be exponential decay. It's not negative. R is negative, but this also means, keep in mind, and this would be a 1, right? This would also mean y equals 1 over e to the 2x power. So as x increases, you're doing 1 over e squared and 1 over e to the 4th power. You know, whatever you're doing there, your numbers are getting smaller as time goes on. So it is exponential decay. I'm going to be using a graph that looks like a DISA. Can probably get it probably a little bigger like that. So with that, let's go to our graphing calculator. And I didn't show you the graph of this last one, by the way. It would have looked like that. Just takes off, right? Super, yay, nice and tall. This one right here, e to the negative 2x power, like that. We can look at it on the graph. It's going to have decay and going to go downward that way. We can do some things to our window if you really wanted to kind of see different effects. I don't really care about y values that are negative, so I'll just go just slightly negative there. So let's look at a little bit more on the curve, like that, okay? And it goes toward the x-axis. That's the asymptote again. That shouldn't be changing. When we go to the table, we can see some numbers right here. I'll just copy and paste as it is again right now, because we're not going to be able to fit all these points. That's the idea, right? We can only fit so many actually good points on here that these would be them. Now, they might recommend, and I don't know, they might recommend when you do, see this says e to the 2x power, so maybe we should go by increments of 0.5 or something like that to get extra points. I can understand that. Save it for this one, but if there are other ones that become more extreme, we might have to. Y-intercept is 1, once again. There is decay. When x equals 1, we're at 0.135. That's less than a fifth right there. It's already having that same shrinkage as before. Only this time it's decay, so as we go to the right, it gets smaller. At negative 1, we have 7.3891. 7.3891. Probably about right there. Then it goes up to 54, which is out of reach for us. So it never actually quite hits x equals negative 2 in this window range, but we hit this decay on this graph like this. Here. I tend to do this little half arrow appearance to these graphs just to talk about saying that it has an infinite domain. It does go forever to the right, and it's continuing itself downward, but towards 0. It never actually crashes through 0 like that. That's a pretty graph. Number 17. Y equals 2 times e to the negative x power. Now, once again, if you wanted to do a rewrite of this equation, that would be 2 over e to the x power. So 2 still exists on top, if that matters. But this will be decay because r is negative 1. So this is exponential decay. You're going to see something similar to what you saw in the previous graph, only this time twice as tall. In a way, there's no 2 this time on the thing. So maybe not twice as tall. Twice as tall as its parent function of decay. So if we go to this one, y equals 2 e to the negative x power. The graph itself, like this. To you, you're like, what's the difference? It's slightly different. When we look at the table, you might see more of a difference here in what points we can plot and fit. I'm going to say this is a good set to look into. We're going to copy paste this, and I need to get the other graph stuff set. So copy and paste that in. We got that. You know what? I don't need this whole block right there. Hold on. Let me get the other graph axes I was using. Bring it on over. There we go. All right, we'll use it like this here on out. I'm getting another set ready. Okay, so when x is 0, y is 2. Notice that once again, that's our y-intercept right here. So always kind of have that one prepped and ready to go. When x is 1, y is 0.74-ish. About 3/4. When x is 2, we got 0.27-ish, about 1/4. A little more than a quarter. So we got a couple more points there. Then around 0.1 when x is 3. So getting some hits. Now we can also hit -1 and -2, about 5.4-ish. And 14.8-ish. All right. So this graph's going to have a little bit more character than the other ones, and I hope we get more of these as an overall. It's tougher to do the really tall graphs, but this one has just enough height, just enough tallness, just enough steepness that we can actually see the effect of the curve and exponential decay. Once again, the asymptote, ladies and gentlemen. Okay, number 18. More of the same, more of the same. Y equals 3 times e to the 2x power. This is where I might consider not only either a scale change, probably not a change in scale, but rather go by different increments, maybe increments of 0.5. I'd say as long as this number is more than 1, let's go by increments of that number, if that makes sense. I'll show you what I mean when we actually do this next graph. First of all, let me paste this set of graph axes in so we know. Second of all, we're going to call this exponential growth because that's a positive 2. It's a positive number. And let's go to our graphing calculator. 3e to the 2x power will look like that. The graph, sharp as is going to take off this way. Super sharp. This time for the table, because it goes by the exponent here's 2, let's go by every 1/2. I'll just put 1/2 because that way we'll put 1/3 when we're ready on the other ones. So, whoops, not graph. Let's go to the table. And let's build around x equals 0 as the middle. Now you can start to see more of what's going on a little bit better for points that are worth plotting. All right, so for points that are worth plotting, you can kind of get an inkling of it here this time. This is right here like that. Now we're going around every 1/2 for x to get significant points out that we can fit. Remember, 3 is the y-intercept, which is why we have 0, 3. When x is 1/2, we're at 8.15, so 6, 7, 8.15, so 1/2 of the way in. And then at 22, that's already out of reach. 18, 19, 20, 21, 22. I mean, it goes already tall right there, so it was really worth getting that actual point there. 1.1 is at -0.5, so probably around there. And 0.4 at -1, and 0.15 right there. So we're getting some of the points on the graph, and as it's going super tall up near that top. I'm not going to actually hit that top. I do want to hit this point, though. There we go. All right, that was actually very helpful for me to get those ones based on what we had on the graph there. All right, there's our exponential growth. There's the asymptote we approach as we go to the left, and we're taking off from as we go to the right. And we move forward. Number 19. Y equals 0.5 times e to the x power. All right, this will be a helpful graph for us. We can fit some more points. I'm going to go back to a table change of 1, every 1. Let's get this graph ready. Now, r is 1, so it is going to be exponential growth. We're going to get a little bit more of a curve since there is a vertical compression based off this 0.5. This 0.5 also, remember, by the way, is our y-intercept. That's at 1/2. Now, this is half the heights of the typical 1e to the x power graph. So the next one should be half of 2.7-ish and half of whatever e squared is, around 3 something we'll eventually get. So let's go to the calculator. Let's do 0.5 times e to the x power, like that. We'll go a standard old table set. Let's start around -3 and go by 1 so we can see what's going on around there. Actually, let's first look at the graph. So the graph is going to a little more slowly take off that way. We get a lot more curve on it. So it looks like we're going to get values a little bit better within range on, let's go down a little bit more. All right, well, we can't really fit the 4, but this is going to be a good set of the table that we can plot some points on. We're going to like this graph a little bit more, you and I. Okay. Paste, please. There it is. Okay, I already have 0, 0.5. Let's get 1, 1.35, so, okay. 2, 3.6, that's half of e squared. 3.69, so about 3.7. Oh, I'm sorry. That was 2.6 something. Let's get up to here. 3, 10 around 10. It's a little bit more than 10. That 4 out of reach, okay? On the other side, -1 is a little less than 0.2, a little less than 1/5 of the way, and then it's really shrinking at that point. But we do get a little bit more of the curve, which is nice. We're going to hit 27 up there, about 10 away still. Not quite hitting there yet. Oh, that's a nice one. I've been pretty good on my curve so far. Haven't really had to hit the undo button. I'm kind of curving up at the end, or so it looks like. I'm not trying to, but it's supposed to be curving right toward the asymptote there. Looking very suave. Number 20. Okay, there's some vertical compression, but then given the -3 on that decay, by the way, it still will have some good height to it as x increases by 1 each time. So it'll have a sharper increase with some compression involved. Now, there is exponential decay. The y-intercept is 0.25. That's a quarter. Let's start by just plotting that point by general knowledge of what's going on there. So we are just a quarter way up from 0 on the y-intercept, and let's get the rest of the graph going. We'll do 0.25, again, is 1/4, times e to the -3x power. When it comes to my table set, let's now increase by 1/3 each time just to kind of get some more points in there. I don't know how valuable it'll be for us to, let's start around 0. I don't know how valuable it'll be for us, though, officially to plot 1/3 as points. I just feel like that's where we can get some of the points really going on. So, yeah, cool. You can see that even before -2, we kind of cross a threshold that we can't really see much on. So I'd say probably these points here. I know it's weird to look at as decimals. I tried to make it say fractions, but it didn't look like it was going to. So the 0.3s are 1/3. The 0.6s are 2/3 of some kind, okay? So just to get some of the points in. Oh, and let me show you the graph as well. So on this graph, decay, okay, sharp decay with some compression involved, and it hits that 1/4 point right there pretty quickly. So again, when we go to this, what we can plot here, we have 0, 0.25 already. When we go just a third of the way over to 2 right here, we're already at 0.1-ish. So there's that shrink. You can barely even see what I'm plotting there. At -1/3, we're still at about the 2/3 range right there. And at -2/3, we're at 1.8. And then at -1, we're at 5. And then 13 is the last one I can really hit at this -1 1/3. 13.65. Before it goes out of reach, even at -1 2/3, it already goes out of reach. So we're going to look at something that really appears almost straight down. And it's because of those points that I could plot this thing. What I could do on my graphs as well is change scale. Am I going to do that? Doesn't look like it. Just giving you concepts of what you can fit here. It's kind of awkward sometimes graphing E. Sometimes I kind of have questions on how often we should do it. We're doing it 8 times here, and maybe that'll be enough for like our future. But you know, what's being learned is the growth decay aspect under treating E as a number representing 2.7-ish, I suppose. But you know, after this, it's like we felt like we've gotten a good grasp and learning of what it is. But there are some other things, I think, later on that are still going to involve graphs. Okay, with this being negative 0.25, the negative would make it decay. But this decay ain't sharp at all. In fact, with this being a vertical compression and this being 0.25, this is the widest graph we're going to have seen so far. Same with number 22. This looks like it's going to be wider. But let's go to the graphing calculator, and this is one that I'm looking forward to more. So 0.4 times E, because we can get more points and get it wider in general. E to the negative 0.25x. So when it comes to this here, I mean, I'll go by ones just to get some points out, but I'm going to be plotting a few points, it seems, as a whole. Just kind of get ready for that. We'll start from -3 and see what's going on. But for this graph, there will be decay. It's going to really, this widens out actually a lot. This widens out a lot. This widens out a lot more than I thought it would. So let's go from -10 to 10. We're going to do this like the window range on our actual graph that we have. I'm going to go up to 17 and see if we have anything considerable to look at. Yeah, this thing has a lot of points that, not really a lot I can hit on that side, but you can tell, man, we're going to hit some values. Oh, I'm going by 3s. What am I doing? I did this backwards. Let's start from -10 and see what's going on here. So even at -10, it's only at 4 something. Right? So we got a lot of points to hit on its way down. 0.4 being the y-intercept. So let's do this a couple ways here. I'm going to go by 4s because the 0.25. I'm going to start at -12 so I can hit that 0. Actually, I'm going to start at -10. We already know that when it's 0. We already know what it is when it's 0, and we don't have -12 on our thing. So when it's 0, we hit 0.4. We're going to go to this table. We're going to hit some of these other points along the way. Like that. Okay, so I'm going to paste this guy in here. We'll plot some of those. Maybe it's a little too small. Let me get my other graph paper again. Hold on, I lost it on this page. There it is, it's on the side. Okay. Okay, so when x is 0, y is 0.4, the y-intercept. So we have this guy, and you see the decay action. When x is -10, we have 4.873. Really close to 5. When x is -6, we have 1.79, so 1.8. And at -2, it's 0.65. And then at +2, about a quarter. And then getting pretty small at that point. At 6, getting pretty small at that point. Less than 0.1. So not very much decay, but very much appearance of decay. You get a good widespread of decay. And it's interesting that we didn't really get an in-between of not too much curve and not too little curve. I think this last one will be the best happy medium because it's not as compressed. It'll be growth. Number 22, last one. Getting this ready just in case I lose it later. So number 22. Y equals 0.6 times e to the 0.5x. That's exponential growth. Given it's a positive number, it doesn't matter that it's a fraction or a decimal. It's exponential growth. Let's go to the calculator. I'm going to go by 2s this time because of the 0.5. So with that in mind, let's still start at -10 and see what's going on as we go by 2s. First, let's look at the graph. So it's going to be growth this time. Oh, this is the most ideal curve for us, I believe. Best wide range of values to hit. So, -10, too small. best range is probably around here for us, from -4 to 8. Granted, we can't fit the 8, but that's just good knowledge that we can't. That helps us going. So I copied it. I'm pasting it. And we're going to graph it. Set growth. 0.6 is the y-intercept, as expected. When x is 2, we have 1.6. Oh, 2, not 1. When x is 4, we have 4.4. 3. When x is 6, we got 12. 12.051. Is that x equals 6? I think so. And at 8, we run out of reach. It's probably double our height. A little less than double our height that we have here. -2, a little less than a quarter. A little more than a fifth right there. And at, whoops, that's not -2. And at -4, kind of really zero-ish. All right, that's a nice looking curve, though, to graph. Let's see if we can get that one going. Now, at 7, we might be able to hit something that we can see. That's reasonable, but not at 8. All of my curves have been really good, though. I'm proud of myself. Oh, no. Oh, no. Spoke too soon. Really approaching 0 there. Okay, that's my favorite of the curves. I'm glad we got to do that last one there. A little slight exponential growth. When it comes to money, I hope it increases faster than that, but I'm going to take that for what it is as a graph. Okay, number 23 through 26. Match the function with its graph. Explain your reasoning. My explanation will probably be verbal with you guys, but y equals e to the 2x versus, I want to look at all these, versus y equals e to the -2x, because sometimes it's not about which one's the right number. It's about how can I eliminate which ones they aren't based on what we see and what we're comparing to. For e to the -0.5x and y equals 0.75 e to the x. Okay, when it comes to this, okay, so here's what I'm going to do. I'm going to play process of elimination in a way. I'm going to say A, B, C, D. Hold on. A, B, C, D. And I'm going to eliminate those which it can't be for each of these problems and then talk about which answer is going to be as a result of that. So it's kind of a different form of talking about them, but let's just do these all at the same time. So on number 23, y equals e to the 2x. Because it's growth, we know it can't be A or B. A and B are out based off growth. On number 24, with this being negative, it has to be decay, so it can be A and B, and it can't be C or D. On number 25, also decay, can't be C and D, and 26, growth, it can't be A or B. So that's based off growth or decay. Now, when it comes to intercepts, intercepts will probably answer the rest of the way, to be honest, but we can also talk about other portions of it, such as in 26, 0.75 is more compressed than 1, and this 1 is more compressed than 2 when it comes to overall growth. So 23 versus 26, this is going to be a sharper looking graph with a y-intercept of 1 versus the other one, a smaller looking graph with a y-intercept of 0.75. So this one's going to be C because the y-intercept of 0.75 and not as sharp as D for this one because also the y-intercept. So again, y-intercepts, this number 1 we can see right here. And this number 0.75 we can see right here. Okay, those intercepts will be telling of that. They'll also be telling on these other ones. This y-intercept of 4 means this graph is going to be B. And then this one here is going to be A as a result of the y-intercept being 1 as well. So you could probably reveal everything from the y-intercepts alone except for 23 versus 24. And then 23 will be a growth graph and 24 will be a decay graph. Notice, by the way, how 23 and 24 are exact opposites of each other. If I take this growth graph, I just hit a hotkey thing that did speech recognition. That was by accident. If I do this growth graph and place it right over the decay graph, you will see the symmetry between these two like that. Heck, I could flip it over and it would like match it, right? So it's the exact same graph but the other way given the negative exponent. That's how that thing works. Multiplication versus division. That's the idea. All right, 23, 24, 25, 26. My explanations were had based off of growth versus decay and y-intercepts. We could also eliminate as we went along. Numbers 27 to 30. Use the properties of exponents to rewrite the function in the form a times 1 plus r to the t or y equals a times 1 minus r to the t. Then find the percent rate of change. Okay, so for these problems here, I should probably write the number first. Number 27, y equals e times negative 0.25 to the t power. As a reminder for our properties, that also means e times negative 0.25 times t. And as long as you have a product there, we can do an exponent raised to an exponent, so like to the t power there. You can see because the form is a times 1 plus or minus r to the t, we're going to have to utilize that in this way. Now, when it comes to a is the number that's in front of here. That's 1. So that part's not really used in any sort of way to determine a, but we got to determine r by turning e to the negative 0.25 into a number. Figure out if it's a growth or decay. It should be a decay, so it's less than 1, and figure out what we're subtracting from 1. So the calculator is going to help me a little bit here. I'm going to go to the calculator. I'm going to type e to the negative 0.25, oh, not 0.025, negative 0.25 power, and we're getting this number here, 0.7788. I'm going to round to 4 decimal places each time because I believe the book probably would have done the same thing. So this equals e, and I don't know, we could probably say equals, but that's fine. But equals 1 times, and I'll leave the 1 out there for now, 0.7788 raised to the t power. As far as something times something to an exponent, just like that, that's what this is. But we got to do it as 1 plus a number or 1 minus a number. Clearly, this is 1 minus a number. To figure out what that is, do 1 minus this number. 1 minus this number gives you 0.2212 when rounded, 0.2212. So this whole y equals, I'll just put equals. I hope that's okay. 1 times 1 minus 0.2212 raised to the t power. Now, why would we write it in this form as opposed to just this form? Because this form tells you what percentage decrease something is from 100% as an overall over the course of time, given this interest, whatever it is that we're talking about for this thing. There's the equation in the form. The percent rate of change is a 22.12% decrease. Or decay, or whatever you want to call it. I don't know if I want to say decrease or decay, because the graph things, we might want to say decay. Decrease is fine. You know, it's an either or case when we're talking about those, right? So I'll just say a decrease for that. Okay, that's number 27. Number 28. Y equals e. It's very, very similar to this last one. Y equals e to the negative 0.75 t power. Once again, we can split this up as e to the negative 0.75 raised to the t. And once again, there's a 1 in front here. 1 times. And we have, let me just do the calculator. Like, you don't need to see the calculator portion. You don't need to see what I'm doing here. I'm doing negative 0.75 in the exponent. This number to 4 decimal places is 0.4724. Now, we expected a decay. To what amount? Who knows? And I'm going to do 1 minus that number, rounded to 4 decimal places, and that's going to be y equals 1 times 1 minus 0.5276 to the t power. So there's the equation, which means we have a 52.76% decrease. All right, number 29. Y equals 2e to the 0.4t. All right. So the same split can happen inside of here. Now I'm going to keep 2 on the outside. That's basically our a value. This is e to the 0.4 raised to the t power. So I'm going to do e to the 0.4 power, positive, e to the 0.4. And I'm getting 1.4918. Whoops, not e. 1.4918 raised to the t power. So we're adding 0.4918 to 1. This is 2 times 1 plus 0.4918 to the t power. Because that separation, and in that form, we can determine that our percentage increase here, the percentage rate of change, we are increasing 49.18% from 100%. We have a principal initial amount of 2 2 something, $2, to whatever it is, but we're increasing that much over that time based off that rate of change with that natural growth from e. And then number 30, y equals 0.5 e to the 0.8t. Once again, 0.5 would be like your e value. Give me 1 second. Let's separate to e to the 0.8 times t. That's a positive r value. That will make this growth again, even though the number is less than 1. 8. 2.2255. So this is 0.5 times 2.2255 to the t power. Now, that's still 1 plus something. It's just 1 plus a larger number, 1.2255, which means this is a pretty substantial growth here. Remember, e to the first power should be 2.71, whatever. So this is a 122.55% increase. Money's looking good, yo. Money's looking good. I'm loving it. Okay, numbers 31 to 34. We're going to use a table of values or a graphing calculator to graph the function, then identify the domain and range. Now, these are ones that I almost feel like I could do on my own in some capacity. Given that I know some of my values for E, I almost feel like I want to do some of these on my own with it. This time they say use the graphing calculator. Kind of last time I used it, right? But it says identify the domain and range as well. I want to talk about these as far as predictive values, as well as why the graphing calculator says what it is before we actually graph it itself. So this has to do with some of your shifts. If I speak as a whole on this thing here, in between here and here, we're looking at a form when we do our shifts, y equals ab to the x minus h plus k. Now, you've seen things on h and k before. H is horizontal translations, k is vertical translations, h is opposite sign, k is same sign. Now, b is your growth factor, a is your y-intercept. So when you're looking at these numbers, k is 0, a is 1, b is e, what you multiply by each time, and h is 2. So you would take whatever function you'd have as a graph. Well, a is your y-intercept if there's no translation. A is your reference point above the asymptote here. So when it comes to graph, shoot, are we going minus sometimes? We're going to have to do the taller graphs these times. When it comes to this graph right here, here's some of my expectation. First of all, I still have an asymptote at y equals 0 because of the k value being 0. There's no vertical shift on this. Secondly, normally I'd say my y-intercept is 1, right? But this is now shifted 2 to the right. That's what that little h value of x minus 2, whatever, that's what that's doing. So this is going to be shifted 2 to the right. Every time x increases by 1, we're going to multiply another e to our name. So 1 times e is e, and e is about 2.7. So I'm going to get a point right there. E squared is around 7.4. These are just numbers that I've seen over and again. And e cubed we saw is about 20.1, so I can fit about right there. 1 over e is a little more than a third, probably like that. So you can start to see a shrink like this. I already know this is the graph before going to the graphing calculator. So just kind of giving you some points there. The reference point is where I begin, though. It has to do with A and H in comparison to K. B is treated with every other point afterward based on our distance from K, distance from the asymptote. So I already know that that's going to be the graph. We can go to the graphing calculator and take a look at it as well. I want to make sure to get the same looking window range. So let's go to there. Let's go y equals E. See, these are the ones I wish we were graphing. These are the ones I know how to do a little bit more instead of random decimals and stuff like that. To the x minus 2 power. Let's get a good looking window range. That is actually a good looking window range. And you're going to see the same bits. It's going to cross at 2, 1. Boom, right there. So when I go value and I choose x equals 2, you're going to see a y value of 1. Boom, like that. Okay. And so on and so forth, right? I can go to the table. Oh, these are going by 2s. Let's go by 1s. I can go to the table. I can go by 1s. And you can see the numbers that I said. 2.7-ish, 7.4 when rounded, 20.1 when rounded, and a little more than a third over on this side. So those are the points. That's the graph. Once more. And I had it drawn over here on this side. Now they're going to talk about domain and range or ask about that. Domain is all real numbers. There's no reason any of these won't be. You can plug in any value for x. Range is based on your asymptote. your y is greater than 0. It cannot be 0 in this case. It's going to have to stay above the asymptote. And as long as there's no vertical shift, it's going to be greater than 0 as long as these are positive functions. All right, number 32. Let's continue on that warpath. I'm going to try and get the drawing beforehand, do the best I can. My only trouble is with 2 times e and things like that, but I'll do the best I can. Y equals e to the x plus 1 power. I think what I'm going to do on this one, let me take the graph we just did on the previous one, copy and paste it, and do a shift on that thing. So copy that, paste that over. So this is going to be the same graph in a lot of different ways. The y-intercept, well, not the y-intercept, but the we're going to start 1 unit above the asymptote, and the asymptote is again going to be at y equals 0. There's no change there. We're just going to take this and shift it over because now h is -1. So we're going to shift this over so our reference point is right here instead at -1. When x increases by 1, we're still multiplying by e. Remember, this is 1. That's why we start 1 up. And plus 0. That's why we start down here. When x increases by 1, we multiply by another e. So e is here, and e squared is here, and e cubed is somewhere up there. So the graph is going to look like this. It's just a shift. It's just a shift. So the domain and range will be the same as well. Let's go to the graphing calculator and take a look at that. Plus 1, and you're going to see the same appearance of this. Crossing out about right there, boom, and going up. And hopefully you can see that mimicked on my graph here. Domain is all real numbers. Range, y is greater than 0. All right, numbers 33 and 34. These have a couple changes for us. Now, these ones do not have horizontal shifts, but it does have a vertical shift. Vertical shift affects asymptote. Asymptote is the bottommost part of these graphs that we're actually going to hit. So this asymptote is at k equals 1, or y equals 1, because the k value is 1 like that. And everything we do is going to be in relation to the asymptote. Now, because there's no h shift here, this will be our y-intercept. We're going to go 2 units from the asymptote, not from the x-axis, but from the asymptote, when we have an exponent of 0. So we're going to go 2 up from here, like that. And we're going to multiply 2 by e every time x increases by 1. Now, 2 times e, this is where I'm going to have a little trouble. 2 times 2.7 is around 5.4. So we're going to go 345.4 from the asymptote, not from the x-axis. 2 times e squared is 2 times around 7.4, so around 14.8 or 15. We're going to get really close to that 16 number right here. Really close to that number right there. And that's about as tall as I can get, obviously, before going anywhere else. 2 divided by e, you know, what's 2/3, right? It's around 0.6, so it's a little more than 0.6 up from the asymptote like that. So we're going to get some points like that. We're going to use the graphing calculator regardless to get it, but this should be the appearance of this graph here. Now, what you're going to see on the graphing calculator is a curve that does not go down to the x-axis. It's going to be flattening out. You're going to see around y equals 1. That's what we're going to see instead. They're not going to show you a dotted line. We can make our own, but they're not going to show you a dotted line on this thing. So if I do y equals 2 e to the x, and my plus 1 has to be on the outside like this, once again, it's going to be above the x-axis right there, like that, and then curve its way up. It crosses through 0, 3, 2 up from the asymptote, and it has the takeoff right there. I can make a dotted line if I make y equals 1 and change this thing to, those are inequalities. There, a dotted line like that. I can make a dotted, oh, it didn't make it dotted. I tried to make a dotted line. It didn't seem to want to. Maybe it does it if it's not, yeah, I don't know if I can make it actually dotted. Oh well, but that's my asymptote. Okay, that's the asymptote there. Anywho, I tried. Okay, but there's the graph. Now domain and range. Domain is still all real numbers, no change, and there won't be one. Range is going to be y is greater than 1 this time. It's basically compared to the k value. We have to stay above 1. And then number 34, this is why I need to use the full graph thing for this one. Oh, I never changed to 33. I'm sorry. That was 33. Number 34, the reason I had to change to the tall graph is because of number 34, because of our k value this time being -5, which is probably good news for this 3, because that's going to triple our heights of our values. -5 still will be the k value, though. So we're going to be y, not y-axis, y equals -5 will be our horizontal asymptote down here. It's shifted 5 units downward. It's not horizontally translated, so this will be our y-intercept 3 units up from here. And every time x increases by 1, we multiply our distance by e. 3 times e is where I probably want to use the calculator a little bit more. We're going to do 3 times e to the first power. I want to do 3 times e squared. I want to get both of these two numbers here. 3 times e squared. Now keep in mind, these are the distances from the asymptote. The asymptote's -5. So what's about 8 up from -5? 3. What's about 22 up from -5? About 17. So these are just a little bit above 3 and 17 for our next couple points that we can plot here. So here I can plot, so 8 units up from there, again, about right there. And 17 is the very top. So the next one, e squared, is about there. Now 3 divided by e is a little more than 1 because e is a little less than 3. I know that. And then divided by another e, about a third of that. You know, we're getting there. So you can start to see some of the shrinkage. Now I'm going to draw the graph. Oh, is that black? I'm going to draw the graph, and then I'm going to go to the graphing calculator to confirm what it is that we just found. My curves have been on point. Woo. I want to woo loudly. Woo! Sorry if that was too loud for you guys. All right. My curves have been on point. Those feel good, man. My parabolas in comparison have really suffered. Okay, let's take a look at that as a whole. 3e, that's a plus. 3e to the x minus 5 power. This graph, I have to change the window range this time. I got to go down to at least -5. How about -7? For y here, it's going to start from that bottom. Starting from the bottom now I hit and curve up and on through. So this is y equals -5 is the asymptote on that. Domain of this is all real numbers. Range of this is y is greater than -5. Okay. Not too many questions to go. A lot of them graph focused. So the rest are probably word problems. A lot of things with continuously compounded interest. Probably one of those how do you see it things with the graph. We'll check it out. So I thought there'd be more focus on them, but maybe not. All right. I want you to read this for a second. Take a sip of water. All right, we have something for a balance of a house as it grows over time. We got h equals 3,224 times e to the 0.05t. That does mean growth, even if minimalistic growth. It's 5%. That's actually normal. The graph shows the balance in the education fund over time, which account has greater principal. Oh, that's not house, it's house fund. Education fund versus house fund. Which account has greater principal? Which account has a greater balance after 10 years? So this one's principal amount is this guy. This is based off the formula APERT. A equals P e to the RT. R is the interest rate. P is the principal amount. A is the accrued value over that time t in years. Your principal amount here for house fund is $3,224. For the other one, the education account, I'm going to copy and paste that graph. For the education account, the principal amount on this guy is when time is 0, so that's $4,856. I'll put PE for this and PH for the other one. What wins, the pH scale or physical education? Physical education wins to start with. Which account has a greater balance after 10 years? Let's find out here, because I kind of ran out of room. 3,224 times e to the 0.05 times 10. 0.05 times 10 is 0.5. So if I wanted to just get things a little bit faster rolling here, I'll just do 3,224 times e to the 0.5 power. That'll help me out. And I'm getting $5,315.48 about. Now, for PE at 10, we're looking in the $7,000 range. $7,000 range. So this thing has more after 10 years. So this is 10, comma, 7,000. I don't know, 7,250. It's kind of like the one from the example that we had in the book at the time. It's somewhere there. Now, did it say which one got more? No, which one has a greater balance? So after 10 years, this one has a greater balance. Did it increase more over that time? This went from about 4,800 to about 7,250. That was probably one about 2,500 up. This one went about 2,100 up, so this one also added more over time. Education account is just flourishing compared to the house fund. Education fund. All right, so education fund has greater principal and greater balance after 10 years. House Fudd. Elmer Fudd. Number 36. Tritium. You guys know where tritium's from? Well, it's a movie reference. Film came out in, I think, 2004. A villain was wanting the precious tritium to fuel their nuclear fusion project. Nuclear fusion project? Come on. I need the precious tritium, Harry. Tritium is an isotope of hydrogen that can be used to illuminate watches. Tritium and sodium-22 decay over time. In a sample of tritium, the amount Y in milligrams remaining after T years is given by Y equals 10 times e to the, here's decay, negative 0.0562 T power. Y sub T. This is tritium. Oh, I shouldn't have a T there because there's a T in the formula. I'll do a capital T. Y sub tritium. Okay. Graph shows the amount of sodium-22 in a sample over time. Let's copy and paste that one. Which sample started with a greater amount, which has a greater amount after 10 years. So no real change compared to the last problem. Just got to plug some numbers in. But now that they both have decay, the comparison is still which is greater in these cases. Now the tritium has a principal amount of 10 milligrams, and the sodium has a principal amount of 15 milligrams. So sodium has more starting at the initial amount, started with a greater amount. After 10 years, sodium, after 10 years, goes from, these goes by 5, so probably about 1 milligram, around 1 milligram. I'm going to say. Let's see how much tritium compares with this. We'll do Y sub 10. So that's 10 times e to the... This times 10 means it just shifts the decimal place up. That's what I spoke on in the previous problem. So negative 0.562. I'm going to use that in the calculator. I got 10 times e, and I have no idea what it's going to be. Negative 0.562. It's around 5.7. So clearly, even if this was around 2 milligrams or so, tritium wins after 10 years as far as how much remains. It doesn't decay quite as quickly as sodium. So sodium's decaying substantially faster than the tritium, which started with less and ends up with more 10 years later. So sodium-22 has a greater starting amount. However, tritium has a greater amount after 10 years. And hopefully you saw the two comparisons of them. Okay, number 37, on open-ended, find values of a, b, r, and q such that f of x equals a e to the rx and g of x equals b e to the qx are exponential decay functions, but f of x over g of x represents exponential growth. Okay, so on number 37, we have an f of x equation. I'm going to write these right above each other so that I know exactly, because I got to divide this later, so I want to think about this division. B e to the qx. So to both be decay functions, r and q both have to be less than 0. R has to be less than 0, q has to be less than 0. However, in order to end up being exponential growth, q needs to be less than r, meaning a larger negative. Because when I have a negative minus a larger negative, that's a negative plus a bigger number, which turns it positive. Ultimately, I need this division to be that. So I need q to be less than r in the way that it's a larger negative number. Now, a and b, let's just make them positive values. We can make them 1, we can make it whatever. Let's do f of x equals, let's say 10 e to the, let's say negative 2x. And for g of x, let's make it simple. Let's do 5 e to the negative, say, 4x, like that. Now, when we That'll be a lot of 2's. That's okay. When we divide these, f of x over g of x, that'll be this over this. Now 10 over 2 becomes 2. And then these subtract. Negative 2x minus negative 4x, which is negative 2x plus 4x, which becomes 2x, positive 2x. 2e to the positive 2x value, or power. So these can be the things here. So when it comes to a, b, r, and q, my final answer there will be a can be 10, b can be 5, r can be negative 2, and q can be negative 4. A and b, as long as they're not 0, I think you're fine with a and b being whatever they are. They can be decimals, they can be negative, although we haven't really dealt with negative exponential growth and decay, so it's better that those are probably positive as a whole. Whatever r and q are, they both have to be negative to first represent decay, and then q has to be a larger negative, which means a smaller number as a whole, and that's it. So this is very open-ended. There were a lot of ways to go right on that one. Number 38, thought-provoking, is normally generally open-ended as well, so we'll see. Explain why a equals p times 1 plus r over n to the nt. Approximate this as n approaches positive infinity. Okay. Well, it's one that you can do through what you saw in the things. I can try and play with the proof a little bit if I still remember how it goes as a whole. It's a little bit tricky to kind of play with for myself. Let's first start with this concept. Let's say that e equals the limit as m approaches infinity, and I'm using m as a different variable because I'm going to replace it with something else given n and r. This would be 1 plus 1 over m to the m power, as we know that e would represent this as a whole. Plug in infinity here and infinity here, we're good. Now we deal with this formula here where we have a equals p times 1 plus r over n to the nt power. Now what we want to do from there is we want to let m equal n over r. Now what we can do here is we can multiply both sides by r, and we get n equals r, m times r, or r times m. Now when it comes to rewriting some of these things, what we can do is a bit of a substitution. Take this same formula here, n becomes m times r there, and let me just scoot this one up a little bit, right there and right there, and we get a equals p times 1 plus, now if n equals m over r, notice if I divide both sides also, if I divide both sides by n, I get r over n, and divide both sides by m, I get 1 over m. So r over n can be rewritten as 1 over m, which we've seen here before. Now, n equals m times r, so m times r can go up here, and this is times t. So as a little bit of a rewrite that we do have here, m times rt can be split up, so it's 1 power raised to another power. This can be p times, and I can have 1 plus 1 over m raised to the m power, and that whole thing can be raised to the rt power. Because e equals the limit as m approaches infinity of this thing right here, now that we're dealing with this a given m approaching infinity on this set, a approaches, or a equals limit as, not limit divided by, limit as n approaches infinity of this thing, right? We're plugging in m in this case, 1 plus 1 over m to the m power raised to the rt power. This will be, this is as m approaches infinity, not n. This is a equals p times, this is e, right? E equals this, p times e to the rt power. So that's the proof. I don't know, they said explain why. That's what I would do for that. That's the idea behind the process, and that's what we get there. It's an interesting rewrite, and that's it. Okay, number 39, writing. Can the natural base e be written as a ratio of two integers? Explain. No. E is an irrational constant. No. E is an irrational constant, which means, by definition, it can't be written. Where's the I? it can't be written as a ratio of 2 integers. Yeah, only rational numbers can do that, and not an irrational number. Okay, number 40, making an argument. Your friend evaluates f of x equals e to the negative x when x equals 1,000 and concludes that the graph of y equals f of x has an x-intercept at 1,000, 0. Is your friend correct? Explain your reasoning. Well, these graphs here do not have x-intercepts. They don't touch 0. So when you're looking at f of x equals e to the negative x power, this graph will get closer and closer to 0 over time like this, but it never actually touches. There's an asymptote. It's not quite that simple of a decay like that, but it gets closer and closer to 0, never actually touches. The calculator will probably say 0 because it kind of gives up over time. It says, I can't compute something that small. But that doesn't mean that it actually hits 0. My friend is incorrect. This is because there is an asymptote. There is a horizontal asymptote at y equals 0, the x-axis. Therefore, this graph has no x-intercepts. It's possible to have an x-intercept if there's a downshift, but there's no downshifts here. Has no x-intercepts. Your the calculator may say 0 because it is an infinitesimally small value. It is an infinitesimally, how do you spell this? Small value. Something that's not to, 0.00000 and 1,000 zeros, right? But that doesn't make it 0. Might as well be, but it's not. Number 41, drawing conclusions. You invest, this is the kind of stuff that I expected us to get more questions on. This kind of stuff right here. I thought with the word problem things we'd be doing a lot of these. Not so much. Anyway, number 41. Here we go. Maybe it's on a different set of problems that I'm just not aware. You invest $2,500 in an account to save for college. All right, I have an initial amount of $2,500. Account 1 pays 6%. R sub 1 pays 6% interest compounded quarterly. Account 2 pays 4% annual interest compounded continuously. Let's just say n equals infinity. Which account should you choose to obtain the greater amount in 10 years? T equals 10. Now let's do t equals 10 after the fact. What I'm going to have first are a couple models. For this model here, we're going to use compounded quarterly. We take 2,500 times, by the way, it doesn't matter whether you start with $2,500 or $1. The answer is going to be the same regardless of which one you choose. This is 1 plus your interest rate over n to the nt power, 4 to the 4t power. This one is apert, a equals p, 2,500, e to the rt power, like that. Now, 0.06 over 4 can reduce. If you want to write that as a whole, like smaller set, is 2,500. 1 plus 0.06 over 4 is 0.015. So this is 1.015 to the 4t, if you want to kind of make it a little bit smaller looking. So when you do t equals 10, this is a sub 1 and a sub 2. A sub 1 is going to equal 2,500 times 1.015 to the 4 times 10, or 40 power. We'll figure that out. And a sub 2 equals 2,500 times e to the 0.04 times 10, which is 0.4 power. So which value is more money? I don't know. I think they're going to want to lean on e being more money and make the argument that c, even though you have a higher percentage, doesn't mean that you get more money as a result. I'm going to bank on it being e based on that alone. So let's go to the graphing calculator, or the calculator, and let's do 2,500 times 1.015 raised to the 40 power. Money. And let's do 2,500 times e to the 0.4 power. Oh, less money. Oh, darn it. All right, so this one, I guess the argument won't be made in that way. Okay, so this is $4,535.05. I guess they didn't make the argument for us. And $3,729.56. So Those are the two different ones that we have there. That's account 1, that's account 2. Which one should you choose? You should choose account 1. That's just over 10 years. Over time, beyond that, maybe you would want to choose the other one, or over less time, maybe you want to choose that one, right? It depends on kind of how that growth thing works as an overall, but that one kind of clearly shows that you want to choose account 1. Okay. 2 more questions. Number 42, how do you see it? Use the graph to complete each statement. Okay, so you see the horizontal asymptote down at -3. So for this part A, we're going to say f of x approaches what as x approaches positive infinity. As we go forever to the right, this graph is going forever up. So f of x approaches positive infinity. Now f of x approaches what as x goes forever to the left? It's not negative infinity. It's approaching the asymptote value, and it doesn't actually hit it, but that asymptote value that's getting closer to is -3, assuming that's our proper, just scales by 1. Y is approaching -3 as x goes forever to the left, and that's how asymptotes work, ladies and gentlemen. That's it on number 42. Finally, number 43, the growth of mycobacterium, tuberculosis bacteria can be modeled by the function n of t equals a times e to the 0.166t, where n is the number of cells after t hours and a is the number of cells when t equals 0, so principal amount. At 1 p.m., there are 30 Mycobacterium tuberculosis bacteria in a sample. Write a function that gives the number of bacteria after 1 p.m. So if n of 0, let's assume that's 1 p.m., does it say, it says when t equals 0. I don't know if that's going to be considered. We'll just call that t equals 0. So n of 0 equals 30, and that's going to be a. So our formula here can be now n of t equals 30 times e to the 0.166t. Did they say anything about noon or something like that? Hold on. By the function as the number of cells. It says when t equals 0. I'll just say 1 p.m. is time 0. Use a graphing calculator to graph the function in part A. Oh, this must be part A, by the way. So in part A, we have that, and here's our model. So time 0 will be 1 p.m., if that sounds good. Sounds good. We're going to go to here. And I got 30 e to the 0.166t, or x. All right, we got to change some scales here. It goes to 30 and it increases. So from 30 onward, let's just choose 20 and go up from there. 20 to, I don't know, 60. I don't know how this is going to grow yet. Let's see. Does it just shoot up? Yeah, that's fine. All right, now here's 1 p.m. 2 p.m. is 1 hour later. 3 p.m. is another hour later, because they're asking next about 3:45 p.m. Describe how to find the number of cells in the sample at 3:45 p.m. It didn't say find them, but it does say describe. Okay, so 3:45 p.m. is 2 hours and 45 minutes after, or 2.75 hours after 1 p.m., which is time 0. So substitute 2.75 for t and find n of 2.75. So that'll be it. I'm just going to substitute 2.75 and figure that out. So that's where I can go back to the graphing calculator. And on the graph, I think we fit 2.75 on there clear as day. So let's go to value and do 2.75, and we'll find out how much Mycobacterium tuberculosis bacteria there is. So 47.35. So n of 2.75 is about 47.36 m tuberculosis bacteria at 3:45 p.m. And I think that would be it and all when it comes to that one. They said describe it, and yet I did a little bit more in getting you. that answer there. All right, guys, so that ought to do it for this one. This is Mr. Robinson. Thanks so much for watching. Listen, I really wish that we had more problems on the continuously compounded interest stuff. We started early with some E stuff and graphing and simplifying, and I hope it was making sense. But coming up next, I think, are things regarding logarithms. So we've done a lot of things on exponential functions in the past. Now we're putting it all together and using inverses of exponential functions to do things on logarithms. So I hope you're going to feel pretty prepared for that. So thank you so much. Take care. I will see you in that next one.